Okay, so we have gotten acquainted with the solar system and how we think it formed. So now I think it's time to move on to planets outside the solar system, referred to as exoplanets. All right, so first let's define terms. So an exoplanet is a planet that orbits a star that is not the sun. This is not an official definition. As far as I know, there's not like a real like official definition, but this is a working one that's good enough to work with. So the first hint of the existence of exoplanets came in 1984, which is actually earlier than most people think, certainly earlier than I thought. So a disk of dust and debris was imaged for the first time around the star Beta Pictoris. So this star is relatively young, only about 12 million years old. There were hints that there was at least one planet orbiting this debris disk, including kind of strange comet paths and a warp in the disk itself. However, it wasn't until 2008 that a planet was imaged and measured to be about 8 times further from Beta Pictoris than the Earth is from the sun. The next exoplanet um, first came almost a decade later, right, in 1992. This was the year that the very first exoplanets were confirmed. So these planets were discovered around a pulsar. A pulsar is a compact remnant of an exploded star that rotates and emits a beam of radiation. So from Earth, it looks like the star is pulsating. The nature of this type of star makes it almost impossible that a planet would be habitable by humans, but it was where the first exoplanets were really confirmed. The first exoplanet to be discovered around a star kind of in its prime, like kind of like the sun, um, is the planet found around the star called 51 Pegasus, and the planet was dubbed 51 Peg B. So 51 Peg B is the first planet to be found around a sun-like star, proving that our solar system is not really unique in the galaxy. This discovery is hugely important for that reason. So these discoveries only mark the beginning of the exoplanet age. Um, so how many exoplanets have actually been confirmed since 1984? Well, it turns out about 5,800 confirmed exoplanets as of March 5th, a little bit, so a few days ago from when you are watching this lecture. There are over 9,000 exoplanet candidates. So these haven't been confirmed yet. We just kind of think they're there. And there's almost 4,500 distinct planetary systems. So a lot of these planets are not alone around their star, right? They're actually in a system of two or more. So there are several methods we can use to detect exoplanets, but the vast majority of exoplanets have been detected by um, two methods. It's the transit method or the radial velocity method, but there are a couple more that I will go over in this lecture as well. So first, let's talk about the transit method. Uh, so with this method, astronomers use changes in the brightness of stars to deduce the existence of a planet. So here is what happens. Like we can measure how bright a star is really, really well, like with a lot of precision. So that means that we can also measure little bitty dips in brightness. So a planet orbiting its star can cause a measurable dip. A planet crosses the face of the star. Some of that starlight is blocked and will produce kind of a characteristic feature in the light curve. So this is what we might see. We're measuring a star. There's an unknown planet going around it, and suddenly that planet is in front of the star, blocking a little bit of light. So the light curves that we look at look something like this. So the vertical axis is the brightness of the star, and the horizontal axis is time. So the light curve is just how bright a star is over time. During most of the planet's orbit, it's not blocking out any starlight. However, once the planet starts to transit the star, there's a small dip in the starlight that we can actually measure. So this is a real light curve taken by JWST of a gas giant exoplanet called WASP 96b. The vertical axis here is still brightness, and the horizontal axis is still time. So as the planet starts to transit the star, the light is blocked until it crosses to the other side, right? See, we get this exactly characteristic curve. There are a few things we can learn from light curves. We can directly measure the period of the planet, as illustrated by this light curve right here. So the time measured between the dips is the time it takes for the planet to make one trip around the star. We can also directly measure the transit depth, or how much starlight is blocked. So if we know the transit depth and the diameter of the star, we can calculate the diameter of the planet using kind of this relationship here. It's a fairly simple, straightforward relationship. The depth of the transit curve tells us something about the size of the planet. So as you can see kind of from these examples right here, the small planet produces a light curve that's much smaller than the curve produced by a big planet. We can also use the orbital period of the planet to get an estimate of the distance of the planet from the star. It's not really a simple one-to-one relationship, but there is a relationship between the period and the distance from the star, which that is illustrated right here. And that makes sort of intuitive sense, right? The longer the orbital period, the longer it takes to travel around the star. So, Venus has a shorter orbit than Earth, which has a shorter orbit than Mars. Like that kind of makes some sense. So something else we can glean from this method is what a planet's atmosphere is made of. That is something that we may get to a little bit later on in the course, perhaps. But it's something like if when the planet passes in front of the star, if that planet has an atmosphere, we can kind of measure that light going through the atmosphere. It's a very difficult measurement, but it's something we were able to do. So it gets a little bit trickier, but astronomers can also tell using this method if there is more than one planet orbiting the star by reading its light curve. So let me try to play this video here. Let's see if it works. Okay, so there are 3 planets orbiting this star. So there's a plot of the light curve at the bottom. So the first transit is pretty clear, but then look what happens when the 2 planets transit the disk of the star. So there's an initial dip in light and then a secondary dip. So the reverse happens when the planets kind of finish their transit. The amount of light increases, but not all the way until the second planet kind of finishes its transit. So by parsing these more complicated curves, astronomers can distinguish between the transit depth, the duration, and orbital period for each planet in the system. So the second most common method for detecting exoplanets is called the radial velocity method, or also called the wobble method. So it's a common misconception that planets orbit stars, right? So what happens is the star and the planet orbit a common barycenter, or a center of mass. So if we were to take the Earth-Sun system in isolation, the barycenter would be inside the sun. However, if we did the same thing with the sun and Jupiter, kind of illustrated in this cartoon right here, the barycenter of the sun-Jupiter system is actually out in space between Jupiter and the sun. So you can think of it as kind of a balance point on a teeter-totter. So both the star and the planet will orbit around this center of mass, which will cause the star to wobble. Um, so let me see if I can play another video. It's kind of illustrated in this video here. Like you can see the star actually orbit around the barycenter. We're kind of looking at it from the top down. But what would this look like from a side view? Okay. So there's a lot going on this slide, so let's try to kind of walk through it kind of slowly. So first in the upper left is the orbit of a planet and a star around a center of mass, like we saw on the last slide, right? Right here. So no problem there. So below that is the side view. So you can see both the planet and the star it will move kind of back and forth. Let me see if I can start playing this. There we go. The planet and the star kind of move back and forth. Okay, so this movement has an effect on the spectrum of a star. So that is what kind of this rainbow thing is down here. That's what it represents. So in any spectra, there will be things called emission lines and absorption lines. And these are basically just wavelengths of light that the star is either emitting or not emitting. So in this rainbow, the black lines are the absorption lines. As a star moves along its orbit, we see those lines shift in the spectrum. So measurements of these shifts gives us the radial velocity curve that we get right here. So measuring these shifts gives us a radial velocity. So the horizontal axis on this is time, just like the transit curves, but the vertical axis is relative speed. So as the star wobbles, as it orbits the barycenter, it is constantly moving either towards or away from us. So the short version of this is how the star moves in its orbit changes kind of how we see the star, right? If it's kind of a large planet and we have the star really moving kind of a lot around the barycenter, we're going to see a lot of shift in the spectrum, and the radial velocity plot will really show kind of a movement that we wouldn't expect to see if there was no planet present. So we know that since a star is wobbling, there is something out there making it wobble. Like if there was no planet around that star, it wouldn't wobble like that. It takes a planet to kind of tug on it to make it wobble. So we know also that due to conservation of angular momentum, the planet's orbital period should be the same as the star's orbital period as well. So we can read that kind of right off the radial velocity graph. There's also like a nice relationship between the mass of the planet and the velocity of the star and the planet. So remember, the mass of the planet, that's not really something we can calculate from the transit method, right? So these are really complementary methods of planet detection. We can get mass of the planet from these radial velocity curves. So radial velocity and transit methods are how the vast majority of exoplanets are found, but there are other methods. And one of these methods is through direct imaging. So direct imaging is basically what it sounds like. It's actually getting a picture of a planet orbiting another star. This, though, is extremely hard to do. Planets are very dim in basically all wavelengths compared to its star. So it takes some really special circumstances to do this, but it can be done. But only a handful of exoplanets have been identified in this way. So direct imaging works best for planets that have really large orbits, so they are relatively far from their star, and for exoplanets that are oriented in such a way that the transit method can't be used. Direct imaging is not very good for finding really far away exoplanets, or finding exoplanets by particularly bright stars. But like I said, this has been done before. Like for this system, HR 8799, this is actually a multiple planet system. It hosts roughly or four roughly Jupiter-sized planets, some a little bit smaller, some bigger. Um, I'm going to show this really quick video of how astronomers can actually track the orbit of the planets. It's a series of 7 images taken over 7 years with the Keck telescope. Um, and these planets have periods ranging from 40 to 400 years. So let's see if this will go. Let's see. Yes. Let's see if I can play again. Yeah, these are the planets here. So it's a pretty cool thing. Like we're not getting detailed pictures of them, not like planets in our solar system, but those are a direct image of planets. And it's really cool, but it is pretty hard to do. Okay, so like I said, the direct imaging method, it is pretty difficult to do, and it's having a hard time. We have a hard time doing it. Um, but we have another method that's also extremely extremely hard to find exoplanets. Um, it's very serendipitous, have to have the exact right situations. But with some big ground-based telescopes coming online soon that are designed to do kind of big surveys of the sky, this type of uh, exoplanet finding is possible, and that is through gravitational microlensing. Um, so this method can be used to find very far away exoplanets, exoplanets orbiting far from their stars, and actually possibly free-floating planets. Like planets don't actually necessarily need to be around a star. So how this works, it's a little bit complicated. But gravitational lensing is this phenomenon where you can use the gravity of a foreground object to magnify a background object so we can see it better. Basically, use gravity as a lens. So the image of the background object will be distorted, but other things like its brightness will remain the same. So this method is actually used all the time in galaxy studies because of how massive galaxies tend to be, but it can also be used with smaller objects like stars. And so this is gravitational microlensing. So it's basically kind of on a smaller scale, but the principle is the same. So the microlensing process can occur in stages, as we see here from right to left. So the lensing star, which is the white star, moves in front of a source star, which is the yellow, magnifying its image and creating a microlensing event. So in the fourth image from the right, so about right here, the planet adds its own microlensing effect, creating two characteristic spikes in the light curve. So the light curve will kind of look like this in a microlensing event. this is what gravitational microlensing planetary detection kind of looks like in the wild. Um, so with this particular planet right here, this kind of big long number, it's a subtle observation, right? So we have the entire light curve and then like a little bump right here. Um, and that indicates a planet. Subtle but detectable. So the problem here is that this method is not really repeatable. So microlensing events are unique and they don't happen periodically. They're pretty random and basically impossible to plan for. So I don't think this will ever be like the main way we find exoplanets, but it's still very, very useful. Okay, so I mentioned earlier, we have thousands of confirmed exoplanet detections, and as you might expect, they're not all the same. So astronomers have divided them into four, maybe five broad categories. So there's terrestrial planets, super Earths, Neptune-like planets, and gas giants. So let's start with terrestrial planets. I think we're pretty familiar with terrestrial planets by this point. We live on one, right? These are planets made of silicates and other types of rock, water, and carbon. These planets are also Earth-sized or smaller. Um, and there are comparatively few types of these types of planets that have been detected for reasons I'll talk about in a few minutes. So this is kind of a prototypical one of these discovered in 2017. It's called TRAPPIST-1e. So then there are like the super Earths, and these are also sort of terrestrial planets made of rock and water and carbon, but they're bigger than Earth. Um, this one is was discovered in 2014. Also, it's an artist depiction, not an actual image. It's 1.4 Earth masses. There's also a very similar class of planets called sub-Neptunes, and they're smaller than Neptune, but probably a little bit larger than a super Earth with a larger atmosphere. Like super Earths may or may not have an atmosphere and kind of between the size of Earth and Neptune, but these sub-Neptunes, I'm pretty sure probably have a pretty large atmosphere. The dividing line between sub-Neptunes and super Earths a little fuzzy. But the interesting thing about super Earths or sub-Neptunes is that they seem pretty common, like out in the galaxy, but our solar system doesn't have any. We have Neptune-sized planets and we have Earth-sized planets, but nothing in between. So these types of planets, whether they're super Earths or sub-Neptunes, um, they're true mysteries to us. And then there's Neptunian or Neptune-like planets, and as you may have guessed, these are about the size of Neptune and Uranus. Hydrogen and helium dominated atmospheres with a rocky core. Um, so this is where we can really start appreciating the variation in categories, because in this category, we will also find things called mini Neptunes, which is something less than 4 times the radius of the Earth, but still with a really thick hydrogen helium atmosphere. So this is a very kind of new field, and so a lot of different types of planets um, are also are really common, and we're trying to figure out exactly how these planets all kind of fit together. So mini Neptunes, sub-Neptunes, super Earths, we're really still trying to figure this out. And finally, we get to gas giants, and these are Saturn size or bigger, mostly composed of hydrogen and helium, right? The first planet detected around a sun-like star, that 51 Peg B, that was a gas giant. Um, Peg B is really like half the size of Jupiter. Um, so astronomers would not have detected like any of these types of planets without help from planet hunters, both in space and on the ground. So astronomers have made use of several space-based telescopes in hunting planets. Hubble has helped hunt planets. In the optical and near infrared, there's an infrared telescope called Spitzer. There's a TESS, the Transiting Exoplanet Survey Satellite. It's up there specifically looking for transiting exoplanets, so using the transit method. Um, the Kepler Space Telescope has also been used heavily to identify exoplanets. And then, of course, the James Webb Space Telescope. We can also hunt planets on the ground with ground-based telescopes. We have telescopes at Kitt Peak in Arizona, Keck in Hawaii. In South America, in Chile, we have the Magellan telescopes, and in California, we have the Hale telescope. Okay, so I spoke a little bit earlier about the two main methods of detecting exoplanets. There are, of course, other ways that I went over, but this is a plot a little out of date at this point. But uh, of all the exoplanets detected, yellow is transit method, blue is radial velocity. You can see the vast majority of exoplanets that we've detected are either transit method or radial velocity. But I also want you to notice something else about this plot. So this is a plot of planet mass as a function of orbital period. So orbital period right here on the horizontal, planet mass, and Earth masses on the Y. So there's a line. So right here, this represents where a planet would lie if it was the mass of the Earth. And that is where Earth would lie on this plot. So there are a lot of planets that are much more massive than the Earth, and there are a lot of planets with much shorter orbital periods than the Earth. But there are not a lot with masses and periods that are comparable to Earth, right? We're kind of alone right here. And so why would that be? Like, is Earth just really, really weird? So there is likely a bias in our observations. And when I say bias, I don't mean anything nefarious or even intentional. I mean that our observations, for one reason or another, favor certain characteristics over others. So as long as we're aware of these biases, we can take them into account when we're interpreting our data. The one of the biases is in favor of large exoplanets. So this is kind of a basic problem of astronomy generally, right? Bigger stuff is easier to see. In the case of exoplanets, a large planet is easier to see with both the transit and the radial velocity method. A large planet will block more starlight, and a large planet will cause the star to wobble more than a small planet. Another bias is in favor of planets with shorter orbital periods. So here are the orbital periods of some planets in the solar system. The Earth has a period of 365 days. We're probably familiar with that. Mercury's orbit is 88 days. The outer planets have periods of thousands or even tens of thousands of Earth days. So let's compare this to the TRAPPIST-1 system of exoplanets. Okay. So TRAPPIST-1 is a system of at least 7 roughly Earth-sized planets. So this plot is a schematic of their distance from their star. So basically, it's just kind of like an illustration of their orbits, right? So each one of the colored circles is one of the planets in this system. The axes are basically the distance from the star in AU, in astronomical units, right? Remember, an AU is the average distance from the Earth and the Sun. So even the planet that is farthest out is actually a small fraction of the distance between Earth and the Sun. So it is about 0.05 AU, so 7.5 million kilometers. Um, that is even smaller. All of these planets kind of fit into the orbit of Mercury, right? Mercury is about 35 million kilometers. So these are all extremely short orbits, right? On the order of days, right? Less than a month. So these planets were detected, perhaps not surprisingly, via the transit method. So the faster a planet orbits, the more quickly we can observe patterns in the dimming of the star, making planets with short orbits much easier to detect with this method. So even though we haven't found a lot of like exact Earth analogs, in some ways that's not really what's important. What we really want to find or interested in finding is not just the diversity of exoplanets out there, but we want to find planets in the habitable zone of their stars. So the habitable zone is sometimes called the Goldilocks zone, and it is the distance from a star where liquid water can exist on most of the planet's surface for most of the year. So in our solar system, the habitable zone, it exists kind of just beyond the orbit of Venus, to kind of just before the orbit of Mars. Although if you're being optimistic, you could maybe stretch it out to include the orbits of Venus and Mars. Um, but this region it's going to be different for every single star. Um, because every star is different. So remember that the TRAPPIST system was very close to their star, but their star is dimmer than our sun. And that is why like three or four, I think we may have at this point ruled out TRAPPIST-1d. I think this one is maybe not in the habitable zone, but three to four of the TRAPPIST-1 planets, um, even though they are incredibly close to their star, are in the habitable zone because their star is called an M dwarf, which is one of the smallest and coolest stars there are. And they're also some of the most common stars in the galaxy. Um, so just because a planet is extremely close to their host star doesn't necessarily mean it's out of the habitable zone. That needs to be just measured for each system for itself. And that is what's really exciting when we can find these sort of Earth-like planets in the habitable zone of their star. So this is one of those fields in astronomy. It has grown by huge leaps and bounds in the last 20 years. We have discovered thousands of exoplanets since the first one in the 1980s, 1990s, depending on when you started counting. But there is still a lot left out there to find. It's really one of the most kind of like hopping and hot subfields of astronomy. So that's it for exoplanets. If you have any questions, shoot me an email or come to my office hours.